Welcome to Science for Sleep. Imagine this. You're one of the first humans to step foot on Mars. The red, dusty landscape stretches out before you, and your heart races with excitement. But as you look back at the Earth, you realize something terrifying. You will never return. The journey to Mars, which you once thought would lead to a grand adventure, has now locked you on an alien world forever. The reality of living on Mars isn't just about exploring a new world. It's about surviving in a hostile environment that challenges every aspect of the human body and mind. So, why will anyone who goes to Mars never come back? Let's dive in and explore the shocking truth about the incredible dangers of interplanetary travel. But before we get started, make sure to hit that subscribe button and join us on more mind-bending journeys through the cosmos, where we uncover the hidden truths of space exploration. You won't want to miss this, so subscribe now and let's begin the journey. Now, let's get into it. The distance between Earth and Mars is one of the first and most unforgiving challenges. Mars, at its closest, is about 34 million miles away from Earth, but that distance can expand up to an unimaginable 250 million miles during certain parts of their orbits. For comparison, a single journey to Mars could take anywhere between 6 to 9 months, depending on the launch window. These figures alone highlight one of the greatest problems. Mars is far beyond our reach, physically and mentally. The silence of space holds a secret that humanity has been afraid to speak aloud. Somewhere beyond the blue horizon of our world, past the moon that has watched over us since the dawn of time, there exists a planet bathed in crimson dust. This planet has called to us through telescopes and dreams, through science fiction and scientific calculation, through the whispered hopes of visionaries and the careful equations of engineers. Mars, the red planet, waits in the darkness like an ancient promise, like a second chance written in rust-colored sand. But here is the truth that changes everything, the reality that transforms adventure into sacrifice. Anyone who answers that call, anyone who steps foot on that distant world, will never see Earth again. Not because they don't want to, not because they forgot the blue skies and green forests of home, but because the universe itself has written the rules in physics and distance, in gravity and fuel, in mathematics that cannot be argued with or wished away. This is not a story about exploration. This is a story about permanence, about the ultimate commitment, about human beings who will choose to become Martians forever, knowing that the price of touching that red soil is never touching Earth again. What drives a person to make such a choice? What vision of the future burns so bright that it can outshine the warmth of everything they have ever known? The answer lies not just in the science of getting there, but in the deeper question of why we would terraform a dead world, why we would pour our lives into red dust and thin air, knowing we are planting seeds in a garden we may never fully see bloom. This is the story of that journey, of that transformation, of the brave souls who will carry Earth in their hearts while their bodies become part of Mars forever. The concept of going to Mars and never returning sounds like science fiction, like the dramatic plot of a movie designed to make audiences gasp and wonder. But it is neither fiction nor drama. It is mathematics dressed in spacesuits, physics wrapped in human ambition, reality disguised as impossibility. When scientists and engineers sit in rooms with whiteboards covered in equations, When mission planners map out trajectories on computer screens that glow in darkened offices, they all arrive at the same conclusion through different paths of calculation. Bringing people back from Mars is exponentially harder than sending them there in the first place. The numbers tell a story that the human heart does not want to hear. Every kilogram of fuel needed to escape Mars. Gravity must be carried from Earth, but carrying extra fuel makes the spacecraft heavier, which requires even more fuel, which adds more weight, creating a spiral of requirements that quickly becomes impossible to satisfy with current technology. The rocket equation, that fundamental law of spaceflight discovered long before we ever touched the stars, shows us that for every unit of payload we want to return, we need to send many units of fuel. For Mars, with its gravity, and its vast distance from Earth, that ratio becomes crushing. A mission designed to bring astronauts home requires perhaps 3 or 4 times the mass of a one-way mission. And mass in space translates directly to cost, to complexity, to risk, and to the likelihood of catastrophic failure. This is why serious Mars mission proposals, the ones designed by people who understand orbital mechanics and propulsion systems and life support limitations, increasingly look toward permanence rather than round trips. This is why the first humans to reach Mars will probably go knowing they are pioneers in the truest sense, that they are establishing not a camp but a civilization, not a visit but a home. Understanding why Mars is a one-way destination begins with understanding distance in a way that human minds evolved to comprehend the space between trees in a forest or the distance to the next village, as simply were not designed to grasp. Mars sits roughly 140 million miles from Earth on average. But that number is deceptive in its simplicity because it suggests a fixed gap that can be crossed like an ocean. The reality is far more complex and far more challenging. Earth and Mars both orbit the Sun, but they do so at different speeds and at different distances, like runners on separate tracks circling a stadium. Earth completes its orbit in 365 days, the familiar rhythm of our calendar and seasons. Mars takes 687 Earth days to complete its longer journey around the Sun. This difference in orbital periods means that the distance between the two planets is constantly changing. Sometimes Mars and Earth swing close together in their cosmic dance, approaching as near as 34 million miles, which in space terms is practically next door. At other times, they drift to opposite sides of the Sun, separated by as much as 250 million miles of empty void. This variation in distance creates what mission planners call launch windows, specific periods when the alignment of the planets makes travel feasible with the fuel and technology we possess. These launch windows open for a few weeks once every 26 months, brief cosmic doorways through which spacecraft must pass or wait over 2 years for the next opportunity. Miss your launch window and you are not just delayed. You are stranded in time, watching as Mars and Earth continue their orbital dance without you. The journey to Mars during these optimal windows takes approximately 6 to 9 months, depending on the exact trajectory chosen and the specific capabilities of the spacecraft. 6 to 9 months of floating through the void, of living in a metal tube hurtling through vacuum at speeds approaching 25 kilometers per second, of watching Earth shrink to a blue dot and then to a star, and then to nothing distinguishable from the scattered points of light that fill the black. But traveling to Mars is actually the easier part of the equation. Spacecraft can take advantage of what is called a Hohmann transfer orbit, an elliptical path that requires relatively modest amounts of fuel because it works with gravity rather than against it, using the Sun's gravitational field as a guide rail for the journey. The spacecraft coasts for most of the trip, engines silent, momentum carrying it forward through the frictionless environment of space. Getting there requires one major burn of the engines to break free of Earth orbit and set the trajectory, and another burn months later to slow down and enter Mars orbit or land on the surface. These burns are manageable with current rocket technology. They fit within the energy budgets that chemical propulsion systems can provide. The spacecraft can be relatively light because it only needs to carry the crew, their supplies for the journey, and the landing equipment. Everything is optimized for one direction, for arrival, for the moment when the rust-colored surface of Mars fills the windows and the landing sequence begins. Coming home is an entirely different problem, written in much harsher mathematics. To leave Mars and return to Earth, astronauts would need to launch from the Martian surface, which means they need a rocket on Mars. That rocket needs fuel, lots of it, because even though Mars has only about 1/3 the gravity of Earth, escaping a planetary gravity still requires enormous energy. The rocket also needs to be reliable after sitting on Mars for months or years, exposed to temperatures that swing from warm afternoons around 70 degrees Fahrenheit down to frozen nights of -200 degrees Fahrenheit, exposed to dust storms that can envelop the entire planet, exposed to radiation levels that would horrify engineers designing electronics for use on Earth. This return rocket must launch at exactly the right time to catch the return transfer window, which only opens every 26 months, just like the outbound window. Miss that launch window and the crew must survive on Mars for another 2 years waiting for the next opportunity, consuming supplies and breathing air and drinking water that was carefully calculated to last for a specific mission duration. The return rocket must carry enough fuel not just to escape Mars gravity, but also to perform the necessary course corrections during the months-long journey back to Earth, and then to slow down enough to be captured by Earth's gravity instead of flying past our home world and off into the solar system forever. Every kilogram of fuel needed for the return journey must either be manufactured on Mars from local resources, which requires complex chemical processing equipment and abundant power, or it must be sent from Earth ahead of time, which means multiple cargo missions, each one expensive and risky, and adding years to the mission timeline. The mass calculations become truly daunting when you consider the complete mission architecture. Engineers estimate that bringing astronauts back from Mars would require sending perhaps 10 to 20 tons of return fuel to the Martian surface, depending on the propulsion technology used. Some advanced concepts using nuclear thermal rockets or other high-efficiency engines could reduce this requirement, but even the most optimistic scenarios require several tons of fuel. This fuel must survive the journey to Mars, must survive landing without being damaged or lost, must be stored safely on the surface, and must remain viable for years. If you are sending that fuel from Earth, you need rockets to lift it to orbit, spacecraft to carry it to Mars, landing systems to bring it safely to the surface, all of which have their own mass and fuel requirements. The tyranny of the rocket equation strikes again. To send 10 tons to Mars' surface, you might need to launch 100 tons from Earth orbit, which means lifting perhaps 500 tons from Earth's surface when you account for the rocket stages and fuel needed to escape our planet's gravity. The cost in dollars could easily reach tens of billions for the fuel delivery alone before you even launch the humans. The alternative is manufacturing fuel on Mars using in situ resource utilization. But that requires sending chemical processing plants, power generators, mining equipment, and pumps, and storage tanks, all of which have mass and complexity and failure modes. Either way, the challenge is immense, and that is just the fuel problem. You also need a spacecraft capable of keeping humans alive for another 6 to 9 month return journey, with all the life support systems and food and water and radiation shielding and thermal control and navigation systems that entails. The economic reality reinforces what the physics suggests. Current estimates for a Mars round-trip mission range from $100 billion to $500 billion, depending on the mission architecture and technology assumptions. These estimates make it one of the most expensive endeavors humanity has ever contemplated, comparable to fighting a major war or building infrastructure for an entire continent. For that cost, you could send perhaps 4 to 8 astronauts to Mars and bring them back, assuming everything works perfectly and no spacecraft are lost and no backup missions are needed. But for a fraction of that cost, perhaps 1/5 or 1/4, you could send settlers to Mars one way, establishing a permanent base that grows with each launch window. Each new group of colonists bringing supplies and equipment and expertise. The one-way mission eliminates the massive fuel requirements, eliminates the return spacecraft, eliminates the need to keep everything viable for a multi-year round trip. It allows mission planners to optimize for arrival and survival, rather than for departure. Every kilogram saved on return fuel and return vehicles is a kilogram that can be spent on solar panels, on greenhouse equipment, on tools and spare parts, on the infrastructure needed to build a lasting presence rather than a brief visit. The economics push inexorably toward permanence, toward settlement, toward accepting that Mars colonization means exactly that, creating colonists who live and work and eventually die on Mars, rather than tourists who visit and return. The concept of one-way Mars missions is not new, though it has been controversial every time it surfaces in serious discussion. The idea appeared in scientific literature and space advocacy circles as far back as the 1960s and 70s, during the era when Apollo missions were landing on the Moon, and Mars seemed like the obvious next destination. Early visionaries, like Wernher von Braun, whose designs put humans on the Moon, sketched out massive Mars expeditions involving fleets of spacecraft and crews of dozens of astronauts who would establish bases and explore for extended periods. These early concepts were round-trip missions in theory, but the timelines envisioned crews staying on Mars for months or even years between launch windows, long enough that the distinction between visit and settlement began to blur. The assumption was that anyone volunteering for such a mission understood they were committing years of their life to the endeavor, that they would age significantly during the journey out, the surface stay, and the journey home. As decades passed and Mars missions remained in the planning stage rather than moving to reality, thinkers began questioning whether the round-trip requirement was helping or hindering actual progress toward reaching Mars. In 2004, aerospace engineer James McLean published a controversial paper arguing that Mars colonization should be approached as a permanent settlement project from the beginning, rather than as a series of return missions. He pointed out that historical exploration on Earth often involved one-way journeys, that colonists who sailed to the Americas or migrated across continents or settled remote islands frequently did so knowing they would never see their birthplaces again. The technology for easy return did not exist, but that did not stop humans from expanding across the globe, from taking risks, from establishing new homes in new lands. McLean argued that we should apply the same thinking to Mars, that we should accept permanence as a feature rather than fight it as a problem to be solved. His paper sparked debate in the space community, with some praising the pragmatic approach and others recoiling at what they saw as a callous disregard for astronaut safety and well-being. How could we ask people to volunteer for certain exile? What about their families, their lives on Earth, their fundamental human right to go home? These questions had no easy answers, but they forced the community to grapple with the reality that Mars missions might require a different ethical framework than orbital missions or even moon missions. The most famous and controversial one-way Mars proposal came in 2010 when Dutch entrepreneur Bas Lansdorp founded Mars One, a project that proposed to fund a permanent Mars colony through reality television. The plan was to send settlers to Mars every 26 months during launch windows, with no return planned for anyone. The mission would be financed by selling broadcasting rights to what Mars One claimed would be the most watched television program in history. Billions of people around the world following the selection of astronauts, their training, their journey, and their lives on Mars. The project generated enormous public interest and controversy. Over 200,000 people applied to be astronaut candidates for Mars One, filling out applications that asked if they understood and accepted that the mission was one way, that they would be giving up Earth forever for a chance to be among the first humans to live on another world. Critics attacked the project from multiple angles, questioning the technical feasibility, the financial projections, the ethics of essentially sending people to certain death, since even a permanent settlement would face catastrophic failure modes with no rescue possible. The space engineering community largely dismissed Mars One as unrealistic at best and fraudulent at worst, pointing out that the mission architecture lacked technical depth and that the cost estimates were orders of magnitude too low. By 2019, Mars One had declared bankruptcy and the project collapsed, but it had succeeded in forcing a global conversation about one-way Mars missions and about what people would be willing to sacrifice to be part of humanity's expansion into space. Meanwhile, Serious space agencies and aerospace companies continue developing Mars mission concepts that quietly incorporated elements of permanence, even while officially describing them as return missions. NASA's Design Reference. Architectures for Mars missions, detailed technical documents outlining how the agency might eventually send humans to Mars, included scenarios where crews would stay on the surface for 500 days or more between launch windows. 500 days is more than a year, longer than most work assignments on Earth, long enough to establish significant infrastructure and routines, long enough that the psychology shifts from visiting to inhabiting. The architectures also increasingly incorporated in situ resource utilization on planning for astronauts to manufacture fuel and other consumables from Martian resources rather than bringing everything from Earth. This technology, if successfully developed, would enable return missions by reducing the mass that needs to be pre-positioned, but it also enables permanent settlement even more effectively because the same equipment that makes fuel can make water and oxygen and building materials, can support an expanding colony that never leaves. SpaceX, the aerospace company founded by entrepreneur Elon Musk with the explicit goal of making humanity a multi-planetary species, has been even more direct about the permanence of Mars settlement. Musk has repeatedly stated that the goal is not to visit Mars, but to build a self-sustaining city there, to establish a permanent human presence that can grow and eventually become independent of Earth. SpaceX's Starship spacecraft is being designed as a fully reusable system capable of carrying large numbers of passengers and cargo to Mars. But the business plan assumes that most passengers traveling to Mars will be staying, that the return capacity will primarily be used for cargo or for the small number of people who decide Mars life is not for them and can afford the price of a return ticket. Understanding why Mars colonists cannot easily return requires understanding what Mars is actually like as a place, as an environment, as a physical reality rather than a romantic idea. Mars is the fourth planet from the Sun, orbiting at an average distance of about 142 million miles compared to Earth's 93 million miles. This greater distance from the Sun means Mars receives only about 43% of the solar energy that Earth receives, making it a colder world where temperatures are generally inhospitable to unprotected human life. The average temperature on Mars is around minus 80 degrees Fahrenheit, though temperatures can rise above freezing during summer afternoons at the equator, reaching as high as 70 degrees Fahrenheit in some locations. But those pleasant moments are brief and localized. At night, temperatures plunge to minus 150 degrees Fahrenheit or lower. At the poles during winter, temperatures can drop to minus 200 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the atmosphere into dry ice. These extreme temperature swings happen because Mars has a very thin atmosphere that cannot retain heat the way Earth's thick atmosphere does. The Martian atmosphere is less than 1% as dense as Earth's atmosphere, providing almost no insulation and almost no protection from temperature extremes or from radiation. The composition of that thin atmosphere presents another challenge for human survival. Mars' atmosphere is about 95% carbon dioxide, with small amounts of nitrogen, argon and traces of oxygen and water vapor. There is essentially no breathable oxygen in the Martian air. A human exposed to the Martian atmosphere without a pressure suit would not only suffocate from lack of oxygen, but would also face rapid decompression as the low atmospheric pressure caused gases dissolved in their blood to come out of solution, forming bubbles that would block circulation and cause death within minutes. This means that every moment spent outside on Mars requires a pressure suit, a personal spacecraft essentially, that provides breathable air, maintains pressure, regulates temperature, and shields from radiation. These suits must be reliable enough to bet your life on every single time you put one on, yet durable enough to withstand the harsh Martian environment of fine dust, extreme temperatures, and degrading ultraviolet radiation. They must be repairable with local resources because there is no running to a supply depot for a replacement when you are on Mars. The constant need to wear suits for any activity outside the habitat adds layers of complexity to every task, turning simple actions like walking to another building or collecting rock samples into carefully orchestrated procedures that require time, energy, and meticulous attention to safety protocols. The dust on Mars deserves special attention because it represents one of the most pervasive challenges to long-term habitation. Martian dust is superfine, with particles smaller than cigarette smoke, and it covers virtually everything on the planet's surface. This dust is not like beach sand or desert sand on Earth. It is more like talcum powder mixed with tiny shards of glass. Abrasive and clingy, and capable of working its way into every seal, every joint, every mechanism. The dust is also highly oxidized, essentially rusty, which is what gives Mars its characteristic red color. This oxidation makes the dust chemically reactive and potentially harmful to human tissue. Studies of lunar dust, which has similar properties, show that it can cause respiratory problems and damage equipment when brought into habitats. Martian dust would pose similar challenges, except that Mars has dust storms, something the Moon never experiences. Local dust devils can spring up with little warning, whipping dust into the air and reducing visibility. Regional dust storms can cover areas the size of continents, lasting for weeks. Global dust storms, which occur every few Martian years, can envelop the entire planet in a haze that blocks sunlight and shuts down solar panels for months at a time. During the global dust storm of 2018, NASA's Opportunity rover, which had been operating on Mars for nearly 15 years, lost power as its solar panels were covered and blocked from the sun. The rover never recovered, essentially dying in the darkness of the storm. Colonists would face similar threats to their power systems, to their equipment, to their ability to see and navigate and maintain their infrastructure. Gravity on Mars is another fundamental difference that affects everything about living there. Mars has about 38% of Earth's gravity, meaning that a person who weighs 180 pounds on Earth would weigh only about 68 pounds on Mars. This reduced gravity sounds like it might be pleasant or even fun, like living on a trampoline where jumping and moving requires less effort. In the short term, astronauts would indeed find movement easier and lifting objects less strenuous. But human bodies evolved over millions of years in Earth's gravity, and every system in our bodies, from muscles to bones to cardiovascular function to balance, is calibrated for 1 g of gravitational acceleration. When humans spend extended time in reduced gravity, their bodies adapt in ways that are beneficial for that environment, but detrimental for returning to higher gravity. Astronauts on the International Space Station, which is in microgravity with essentially no gravitational force, experience rapid muscle atrophy and bone loss, losing 1 to 2% of bone mass per month despite rigorous daily exercise regimens. They also experience fluid shifts as blood and other fluids redistribute in their bodies without gravity pulling them downward, leading to vision changes, cardiovascular deconditioning, and immune system alterations. Mars colonists would experience these effects, but likely to a lesser degree, since Mars does have significant gravity, even if it is reduced. However, the effects would accumulate over months and years of living on Mars, and we simply do not know whether the human body can maintain health indefinitely at Martian gravity, or whether there is a slow degradation that cannot be prevented. The unknown long-term health effects of Martian gravity create a one-way trap that is biological rather than physical. If colonists spend years on Mars and their bodies fully adapt to the lower gravity, they might become physically incapable of surviving a return to Earth, even if a spacecraft were available. Their hearts might not be strong enough to pump blood against Earth's stronger gravitational pull. Their bones might not be dense enough to support their weight without fracturing. Their muscles might not be able to hold them upright. They would have become Martians in a physical sense, adapted to their new world in ways that sever the biological connection to their birthplace. This is speculative because we have no data on humans living in partial gravity for extended periods, but it is a real concern that mission planners must consider. The alternative is to provide artificial gravity during the Mars surface stay, perhaps by living in rotating habitats that use centrifugal force to simulate Earth gravity. But this adds enormous complexity and mass to the mission architecture. It requires building large rotating structures on Mars, structures that would need to be powered continuously and maintained carefully. Most mission concepts do not include this level of technology because it pushes the mission beyond what is achievable with near-term capabilities, which means accepting that colonists will live in Martian gravity and will adapt to it with all the unknown consequences that entails. Perhaps the most insidious danger on Mars is one that cannot be seen or felt until the damage is done. Radiation, both from the sun and from deep space, bombards Mars at levels that would be lethal to unprotected humans over time. Earth is shielded from most of this radiation by its magnetic field, a protective bubble generated by the churning molten iron in our planet's core. This magnetic field deflects charged particles from the solar wind and diverts much of the cosmic radiation that streams through the galaxy. Earth also has a thick atmosphere that absorbs radiation that makes it through the magnetic field, so that by the time radiation reaches the surface, it has been reduced to levels that life can tolerate and even thrive under. Mars has neither of these protections. The planet lost its global magnetic field billions of years ago as its core cooled and stopped generating the dynamo effect that creates magnetic fields. Without this shield, the solar wind has been stripping away the Martian atmosphere for eons, thinning it to the whisper that remains today. Cosmic radiation, high-energy particles accelerated by supernovae and other violent cosmic events, slams directly into the Martian surface with no significant shielding. Solar radiation, especially during solar flares and coronal mass ejections, reaches the surface at dangerous intensities. The radiation dose on the Martian surface averages about 24 to 30 rads per year, which is roughly 40 times higher than the annual dose a person receives on Earth from natural background radiation. This might not sound like much, but radiation damage is cumulative. Over years of exposure, Mars colonists would accumulate doses that significantly increase their risk of cancer, that damage DNA in ways that could cause mutations and health problems, that weaken immune systems and accelerate aging during solar storms, when the sun explosively releases massive amounts of radiation. Doses could spike to lethal levels for anyone caught outside without proper shielding. These solar events are unpredictable and can develop rapidly, giving colonists potentially only minutes to hours of warning before dangerous radiation arrives. The journey to Mars also exposes astronauts to significant radiation, with travelers receiving doses of around 30 to 60 rads during the 6 to 9 month transit through interplanetary space, where there is no protection at all from planetary magnetic fields or atmospheres. This means colonists arrive at Mars already carrying a radiation burden, already having used up a portion of their lifetime exposure limit before even starting their new lives. Protecting against radiation on Mars requires living underground or burying habitats under several meters of Martian soil, which provides mass shielding that absorbs and deflects radiation. Early Mars bases would likely be built using natural caves or lava tubes if suitable ones can be found near the landing site, or would require extensive construction to pile regolith, the loose surface material, onto and around habitat modules. This means that living on Mars would have a somewhat claustrophobic character, at least initially, with people spending most of their time in underground or heavily shielded spaces, and venturing to the surface only when necessary, and only with radiation exposure carefully monitored and limited. The romantic vision of looking out large windows at the Martian landscape would need to be tempered with the reality that those windows would be dangerous, that glass provides almost no radiation protection, that the view comes at a price measured in cancer risk and shortened lifespan. Over time, as the colony developed more advanced infrastructure, it might be possible to build better shielding or even to work on generating artificial magnetic fields around habitats. But these are technologies that do not currently exist at the necessary scale and would require enormous amounts of power and resources to implement. For the first generations of Martians, radiation would be a constant, invisible companion, a risk that must be managed and accepted and lived with in the way that humans have always lived with environmental risks they cannot eliminate. The psychological impact of this constant danger, of knowing that invisible particles are passing through your body and damaging your cells, and that there is no escape and no perfect protection, should not be underestimated. It adds a layer of stress to daily life that is difficult for those of us living in Earth's protective embrace to fully comprehend. Every moment on the surface is a calculated risk. Every hour outside is time off your life, a trade of immediate activity for future health. This is fundamentally different from the risks faced by astronauts in Earth orbit or even on the Moon. Those missions are temporary. The radiation exposure is limited by mission duration. If things go wrong, rescue is possible. Or, at minimum, the exposure ends when the mission ends. For Mars colonists, there is no end to the exposure except death, and there is no rescue coming from Earth. They must build their own solutions, must create their own protection, must accept levels of risk that would never be approved for temporary missions. This is part of what makes the commitment to Mars a one-way decision, not just physically, but psychologically. You are choosing to live under conditions that will harm you, that will statistically shorten your life compared to staying on Earth, and you are making that choice knowing you cannot change your mind once you are there. The actual journey to Mars would be one of the most challenging voyages human beings have ever undertaken. A months-long crossing of interplanetary space in a vehicle that must serve simultaneously as spacecraft, life support system, and home. The spacecraft for a Mars mission would need to be substantially larger and more capable than anything used for moon missions or orbital flights. It would need to carry not just the crew, but also all the supplies they would need for 6 to 9 months of travel, including food, water, spare parts, and emergency equipment. It would need redundant systems for critical functions because if life support fails halfway to Mars, there is no turning back and no rescue. The spacecraft would need radiation shielding, or at least a radiation shelter where the crew could take cover during solar storms. It would need exercise equipment to help crew members maintain muscle mass and bone density during the long period of weightlessness or low gravity. It would need communication systems capable of staying in contact with Earth even as the distance grows to hundreds of millions of miles, and the light delay stretches to 20 minutes each way, making real-time conversation impossible. The crew would launch from Earth during a launch window, a period of a few weeks when the planetary alignment is correct for a low-energy transfer to Mars. Missing this window means waiting 26 months for the next opportunity, so mission schedules are rigid, and weather delays or technical problems could result in years of postponement. The launch itself would be dramatic and dangerous, riding a pillar of fire as enormous rockets burn tons of fuel per second to achieve escape velocity. Current rockets are disposable, used once and discarded, which is part of what makes space travel so expensive. SpaceX is developing fully reusable rockets that could drastically reduce launch costs, but even reusable systems need refurbishment and carry risks. Once in Earth orbit, the crew might need to rendezvous with additional propellant tanks or cargo modules that were launched separately, assembling the Mars spacecraft from components in orbit, because it is too large to launch fully assembled. This orbital assembly phase could take weeks and involves complex docking maneuvers and transfers of fuel and supplies between vehicles floating in the vacuum of space. When everything is ready, the spacecraft would fire its engines for the Trans-Mars injection burn, a carefully calculated thrust that accelerates the vehicle to escape velocity and sets it on course for Mars. This burn might last 30 minutes to an hour, the engines roaring continuously as the spacecraft gains speed and breaks free of Earth's gravitational influence. Then the engines shut down and the coast phase begins. For the next 6 to 9 months, the spacecraft would simply drift through space, following the curved trajectory that leads to Mars. Without air resistance in space, no additional thrust is needed during the coast phase. The spacecraft maintains its velocity with its engines silent, following the path carved by the initial burn and the gravitational fields of the Sun and planets. The crew would experience microgravity during this phase unless the spacecraft is designed to rotate to create artificial gravity through centrifugal force, which adds significant complexity and has never been done on a crewed spacecraft. Life in microgravity for months is grueling on the human body and mind. Astronauts on the International Space Station typically stay for 6 months and return to Earth physically weakened and requiring months of rehabilitation even after extensive daily exercise in space. Mars travelers would face the same physiological challenges, but with no option to come home early if problems develop. The psychological challenges of the outbound journey would be as significant as the physical ones. The crew would be confined in a small space with the same few people for months, unable to escape each other or to seek solitude beyond perhaps a small private sleep compartment. Studies of Antarctic research stations, submarines, and space stations have shown that isolation and confinement lead to interpersonal conflict, mood disturbances, and cognitive effects, even in carefully selected and trained crews. The Mars crew would need to be chosen not just for their technical skills, but for their psychological resilience and compatibility. They would need to work through conflicts constructively, because there is no option to separate people who are not getting along. They would need to maintain routines and rituals that provide structure to days that would otherwise blur together in the unchanging environment of the spacecraft. They would need to cope with the growing distance from Earth, watching their home planet shrink in the windows until it is indistinguishable from stars, knowing that the journey is only one way, that they are leaving behind everyone and everything they have ever known. Communication with Earth would become increasingly difficult as light delay grows, with messages taking 10 to 20 minutes to travel each way by the time the spacecraft nears Mars. This means no real-time conversations, only exchanges of recorded messages with long gaps, a form of communication more like letters than phone calls. The psychological burden of this isolation, of being truly on your own in the most literal sense, would test even the most mentally tough individuals. As the spacecraft approaches Mars after months of travel through the void, the crew would face one of the most dangerous phases of the entire mission: the entry, descent, and landing sequence that spacecraft engineers call 7 minutes of terror when attempted robotically, and which would be even more terrifying with humans aboard. Mars has enough atmosphere to create friction and heat during entry, but not enough to slow a spacecraft down safely, creating a narrow margin between burning up from too much friction and crashing from too much speed. The spacecraft would hit the upper atmosphere, traveling at thousands of miles per hour, protected by a heat shield that glows white hot as it converts kinetic energy into heat. The deceleration forces would press the crew into their seats with several times Earth's gravity, a crushing weight after months of weightlessness. The heat shield would ablate away, sacrificing layers of material to carry away the intense heat. If the heat shield fails or the entry angle is wrong by even a small amount, the spacecraft could skip off the atmosphere back into space or could burn up entirely, killing everyone aboard with no possibility of rescue or recovery. After surviving the entry heating, the spacecraft would deploy parachutes to slow its descent through the thin Martian atmosphere. But parachutes alone cannot slow a spacecraft enough for a safe landing on Mars, as they can on Earth, where the atmosphere is much thicker. The spacecraft would still be traveling hundreds of miles per hour when it reaches the lower atmosphere, falling toward the surface with the ground rushing up through the reddish haze. The final landing phase would require rocket engines, either attached to the descent vehicle or part of a sky crane system that lowers the crew module on cables while hovering above on rocket thrust. These engines would fire in a carefully orchestrated sequence, calculated to bring vertical velocity to zero exactly at the moment the spacecraft reaches the ground. Too much residual velocity and the spacecraft crashes. Too much thrust and it might run out of fuel and drop from altitude. The whole sequence from atmospheric entry to landing would take perhaps 7 to 15 minutes, depending on the specific landing system design. And during that time, the crew would be passengers with no control, trusting in automated systems and the engineering that designed them, knowing that a failure at any point means death on a world where their bodies would lie in the dust until they were eventually buried by wind-blown sand. Assuming a successful landing, the crew would find themselves on the surface of Mars in a habitat module that might have landed with them, or that might have been sent ahead years earlier as part of a cargo pre-positioning mission. The first steps onto Martian soil would be momentous, historic, comparable to Armstrong and Aldrin stepping onto the moon, but with the crucial difference that these footprints would not be made by visitors who plan to leave. These are the footprints of settlers, of people establishing residence, of humans claiming Mars as home. The initial priorities would be purely practical, survival-focused tasks that must be completed before any exploration or science can begin. The habitat would need to be checked for damage from landing, all systems tested and verified as functional. Power systems would need to be deployed, likely solar panels or possibly nuclear reactors, to provide the electricity needed for life support, heating, and communications. Water extraction systems would need to be set up to harvest water from ice deposits in the soil or from the trace water vapor in the atmosphere. Carbon dioxide from the Martian atmosphere will be pumped into the habitat and processed to extract oxygen for breathing and to manufacture methane for fuel. Waste recycling systems would need to be activated to reclaim water from urine and moisture in the air, to process solid waste into fertilizer for future greenhouses. Every system would need to be proven reliable because lives depend on them functioning continuously without access to Earth-based technical support or replacement parts beyond what was brought on the mission. The landscape outside the habitat windows would be alien and strangely beautiful in its desolation. The Martian surface is predominantly rust red and orange, colored by iron oxide, with variations to darker browns and tans in areas of different mineral composition. Rocks litter the landscape, scattered by ancient impacts and volcanic activity, ranging from pebbles to boulders the size of houses. The horizon would be surprisingly close, only about 2 miles away compared to 3 miles on Earth, because Mars is a smaller planet with more curvature. The sky would be a butterscotch pink during the day, colored by fine dust suspended in the atmosphere that scatters light differently than Earth's nitrogen-oxygen atmosphere. At sunset, the colors would reverse from Earth's experience, with the sun appearing blue as it sets and the sky around it darkening to deep violet and eventually to black. At night, with no light pollution and minimal atmosphere to scatter light, the stars would be spectacularly bright and clear, appearing to pulse and shimmer with intensity, and Earth would be visible as a blue star in the sky, bright but tiny, close in appearance to Venus as seen from Earth. Looking at that blue point of light, colonists would know that everything they left behind, every person they ever knew, every city and forest and ocean, is contained in that single pixel of distant illumination. The first days and weeks on Mars would be consumed with the unglamorous work of establishing basic infrastructure and routines that would allow the colony to survive. The habitat modules landed from Earth would provide initial shelter, but would be cramped and limited, designed for efficiency and mass savings rather than comfort. Expanding living space would be a high priority, both for practical reasons and for psychological health. The crews would need workshops and laboratories, storage areas for supplies and spare parts, greenhouses for growing food, space for exercise and recreation. Building on Mars presents unique challenges because traditional construction materials and techniques do not work in the Martian environment. Concrete requires water that is scarce and precious, and conventional concrete would not set properly in the thin atmosphere and would be weakened by the temperature extremes. Steel and aluminum could be fabricated if ore deposits could be found and processed, but mining and metallurgy require substantial infrastructure and power that would not be available initially. The most practical construction material on Mars is Mars itself, the regolith that covers the surface. Experiments have shown that Martian soil can be mixed with small amounts of polymer binding agents, or even just compressed and sintered using solar furnaces to create bricks or larger structural elements. These Mars concrete structures would not be beautiful by Earth standards, but they would be functional, and most importantly, they would use local materials rather than requiring everything to be shipped from Earth at enormous cost. 3D printing technology could be adapted to Mars construction, with robotic printers extruding regolith-based material layer by layer to build walls and domes and connecting tunnels. These construction robots could work continuously, unaffected by the cold or the thin atmosphere or the radiation, slowly expanding the habitable space while humans direct them from inside the pressurized environment. Some architectural concepts for Mars colonies envision entire settlements built into the sides of cliffs or into lava tubes, natural caves formed by ancient volcanic activity that would provide radiation protection and structural shelter with minimal construction required. Finding and accessing such features would require extensive surface exploration, and might not be possible depending on where the landing site was chosen, based on other factors like water availability and landing safety. Water would be one of the most critical resources determining the colony's viability and growth potential. Mars has water. Abundant water, in fact, but almost all of it is frozen into ice mixed with soil in the polar regions, or locked in permafrost layers beneath the surface at mid-latitudes. There is also water ice in the polar ice caps, visible as bright white regions covering the poles. But these caps are far from the equatorial regions where colonies would likely be established for temperature and solar power reasons. Extracting water from ice-rich soil would require heating the soil to sublime the ice directly from solid to vapor, then capturing and condensing that vapor back to liquid water. This process requires significant energy input, and the ice content of soil varies dramatically by location, requiring prospecting and analysis to find the best extraction sites. Alternatively, water vapor could be extracted directly from the atmosphere using systems that cool air to condense the moisture. But the Martian atmosphere is so dry that this process would yield only tiny amounts of water for large energy expenditure. It would be supplemental at best, not a primary water source. Every drop of water on Mars would need to be recycled with extreme efficiency, with closed-loop life support systems capturing moisture from air, reclaiming water from waste, and minimizing losses in ways that would seem obsessive on Earth, where water is abundant and cheap. Colonists would become intimately familiar with the sources and uses of every liter of water in their systems, understanding water budgets and conservation in ways that modern Earth dwellers, accustomed to unlimited clean water from taps, can barely imagine. Oxygen for breathing would be easier to obtain than water because the Martian atmosphere, while thin, is rich in carbon dioxide, which can be split into oxygen and carbon monoxide using electrolysis powered by solar or nuclear electricity. This is mature technology that has been demonstrated on Earth and in laboratory settings. The challenge is operating it reliably on Mars for years without maintenance crews and spare parts from Earth. The Mars Oxygen In Situ Resource Utilization Experiment, called MOXIE, flew to Mars aboard the Perseverance rover and successfully demonstrated oxygen production from Martian atmosphere in multiple test runs, proving the concept works in the actual Martian environment. Scaling up from experimental demonstration to life support systems, providing breathing oxygen for multiple humans every day, would require building and operating much larger versions of this technology, and ensuring that backups and redundancy exist so that an equipment failure does not result in asphyxiation. Oxygen production would run continuously, building up reserves in high-pressure tanks that could supply the colony during equipment maintenance or in emergency situations. The oxygen would be distributed through the habitat at partial pressures carefully controlled to match what humans need, likely in an atmosphere that is lower pressure than Earth normal to reduce structural stress on habitat walls, but enriched in oxygen percentage to compensate. Food production would evolve through several stages as the colony developed. Initial missions would bring all food from Earth, freeze-dried and packaged meals designed for long shelf life and minimal mass. These would sustain the crew but would be monotonous and psychologically wearing over time, lacking the variety and fresh flavors that are important to human well-being beyond simple nutrition. As soon as possible, the colony would need to establish greenhouses where plants could be grown under LED lighting, using hydroponic or aeroponic systems that minimize water use. Growing plants on Mars would face several challenges beyond just the obvious ones of providing light and water and nutrients. The Martian day, called a sol, is about 24 hours and 40 minutes long, close enough to Earth's day that human circadian rhythms can adapt fairly well, but the day length affects plant growth cycles. The weak Martian sunlight would not be sufficient for plant growth through greenhouse walls, so artificial lighting would be needed, adding to the substantial power requirements of the colony. The soil, if used directly for growing, is toxic because it contains perchlorates, highly oxidizing chemicals that would need to be removed or neutralized before plants could grow in it. Hydroponic systems avoid this problem by growing plants in nutrient solutions without soil, but they require careful management to prevent disease and maintain nutrient balance. Living on Mars would require not just physical adaptation, but profound psychological adjustment to the reality of permanent separation from Earth. Every human who has ever lived, with the brief exception of astronauts in orbit or on the Moon, has lived with the knowledge that they could, in principle, go anywhere on Earth given enough time and resources. You might never visit Antarctica or the deepest Amazon, but you could if circumstances changed. Mars colonists would lose this freedom permanently. They would live knowing that Earth, with its blue oceans and green forests and billions of people, is forever beyond their reach. They could see it as a star in the Martian sky, but could never touch it, never breathe its air, never feel rain on their faces, or swim in its oceans, or attend a concert, or walk through a city street. The totality of this separation would be psychologically unique in human experience, more profound than any exile or isolation that has occurred in human history, because it is not just geographical but astronomical, not just distant but physically unreachable. The grieving process for Earth would likely be complex and ongoing, not a single event, but a recurring experience triggered by memories and moments. Colonists would miss specific things, not just the abstract concept of Earth, but particular experiences that are impossible on Mars. The smell of rain, the feel of wind that is not filtered through a spacesuit, the sound of birds in the morning, the taste of fresh fruit picked from a tree, the casual ability to walk outside without preparation and equipment, the spontaneity of deciding to go somewhere without checking life support, and radiation exposure. They would miss people, and those losses would be final. If a parent or child or dear friend remained on Earth, the colonist would never see them in person again. Communication would be possible through video messages, but with light delay making real-time conversation impossible, these exchanges would become more like watching recordings than having interactions. As time passed and people aged and eventually died on Earth, Mars colonists would experience their grief from hundreds of millions of miles away, unable to attend funerals or comfort survivors, or participate in the normal rituals of mourning that help humans process loss. The entire social fabric of human life, built on physical proximity and shared spaces and the ability to gather, would need to be rebuilt from scratch on Mars with a tiny population and under harsh constraints. Social structures on Mars would evolve in ways that might seem strange or even alien to Earth-based societies, because the environmental constraints would demand cooperation and conformity in ways that wealthy, comfortable modern societies do not impose. On Earth, if you dislike your neighbors or your job or your city, you can move. If you want to live alone away from others, you can make that choice, even if it is difficult. On Mars, particularly in the early colonial period when the population would be small and resources limited, individual choice would be heavily constrained by group survival needs. Everyone would need to work and work at tasks that the colony needed done, rather than necessarily at what individuals found fulfilling. Someone needs to maintain the life support systems, to tend the greenhouses, to repair equipment, to monitor power systems, to conduct scientific research that justifies the colony's existence, to funding agencies back on Earth. Personal preferences would matter less than competence and willingness to do what needs doing. Conflicts between individuals could not be resolved by separation because the colony would be too small and too interdependent. People would need to find ways to get along, even with those they might prefer to avoid. And the social pressure to maintain harmony would be intense, because discord threatens group survival when the group is small and isolated. The social structure might develop authoritarian characteristics out of necessity, with mission commanders or colony administrators having significant power over individual decisions, because coordinating action in a survival situation requires clear authority. Democratic ideals of individual freedom and majority rule might be less applicable when technical expertise and mission-critical decisions must be made quickly and correctly without debate. The colony would likely evolve a culture that values technical competence, emotional stability, cooperation, and long-term thinking over individual expression or short-term desires. This culture might feel stifling to people raised in liberal democratic societies where personal freedom is highly valued, but it would be adaptive for the environment, shaped by the same forces that shaped tight-knit, isolated communities throughout human history. Over generations, if the colony survived and grew, these cultural adaptations would become ingrained, and children born on Mars would be raised with values and expectations different from Earth. They would be true Martians, not transplants, and their perspective on the one-way nature of their existence would be fundamentally different, because they would have no personal memories of Earth to grieve. Keeping humans alive on Mars would require mastering a suite of technologies at a level of reliability and autonomy that has never been achieved in space exploration. Life support systems on the International Space Station are impressive feats of engineering, recycling water and air, and managing waste in microgravity, but they are constantly maintained by astronauts and regularly resupplied with spare parts and consumables from Earth. When equipment fails on ISS, replacement parts can be launched within weeks or months, and in a true emergency, the crew can abandon the station and return to Earth in a matter of hours. Mars colonists would have none of these safety nets. Their life support systems would need to function for years without spare parts from Earth, repaired using local manufacturing capabilities or improvisation with available materials. Failures could not be tolerated in critical systems, which means massive redundancy, with backup systems for the backup systems, and possibly backup systems beyond that. Every single point failure, every component whose loss would kill the crew, would need to be identified and eliminated through redundant designs or stockpiled spares. Power generation on Mars would likely rely initially on solar panels, which are well-tested technology and can be deployed relatively easily. Mars receives less sunlight than Earth, but still enough to make solar power viable, especially in equatorial regions. The challenge is that dust accumulation on panels reduces their efficiency, and dust storms can block sunlight entirely for weeks or months at a time. Colonists would need to clean panels regularly, an endless maintenance task in the dusty environment, and would need to have enough panel area and battery storage to carry through dust storms. Alternatively, or additionally, nuclear power could provide reliable baseload electricity independent of weather or day-night cycles. Small nuclear reactors designed for space use, called fission surface power systems, could provide tens or hundreds of kilowatts continuously for years. These systems are highly reliable but also controversial due to concerns about nuclear safety, about launching radioactive material from Earth, and about disposing of nuclear waste on Mars. The power requirements for a Mars colony would be substantial, far exceeding what small habitats or rovers need. Life support, heating, lighting, water processing, greenhouse lighting, construction equipment, manufacturing, communications, all of these activities consume electricity, and a colony of even a dozen people might require 50 to 200 kilowatts continuously, comparable to a small neighborhood on Earth. Manufacturing capabilities on Mars would need to advance from simple repairs to actual production of components, and eventually to producing entire systems locally. Early colonists would bring sophisticated equipment like electronics and computers from Earth, because fabricating semiconductors and complex circuits requires industrial infrastructure that would take decades to establish. But simpler items like structural components, hand tools, spare parts for mechanical systems, these could potentially be manufactured on Mars using 3D printing with metal or regolith-based materials. Over time, the industrial base would expand, with each new capability enabling further development. A machine shop with lathes and mills could produce metal parts from raw stock or from metal recycled from damaged equipment. A chemistry lab could synthesize plastics and solvents and other organic chemicals from Martian carbon dioxide and hydrogen. A glass furnace could produce windows and laboratory equipment from silica-rich regolith. An electronics repair facility could refurbish and modify computers and communications equipment, extending their useful life when replacement from Earth is not possible. This bootstrapping process, building an industrial civilization from raw materials with limited starting equipment, would be slow and difficult, but absolutely necessary for long-term survival. The alternative is complete dependence on Earth for every manufactured item, which would make the colony economically unsustainable and vulnerable to being cut off if support from Earth ever ceased. Medical care on Mars would face unique challenges that would require rethinking how medicine is practiced. There would be no hospitals, no specialists, no emergency services that could respond within minutes. Medical emergencies would need to be handled by whoever was available with whatever equipment and supplies were on hand. Colonists would need to be trained in emergency medicine and probably cross-trained so that multiple people could perform critical procedures if the primary medic was incapacitated or unavailable. Certain medical conditions that are routine on Earth would become life-threatening on Mars. Appendicitis requiring surgery would be a serious crisis in a habitat not designed as an operating room. Performed by people who are not surgeons, with limited anesthesia and antibiotics, and no ability to handle complications. Broken bones would need to be set and healed in low gravity, which might affect healing but might also be less problematic than on Earth due to lower mechanical stress. Dental problems would be particularly concerning because severe tooth infections can be fatal if untreated, and dentistry requires specialized training and equipment that might not be available. The colony would need a well-stocked pharmacy, but medications have shelf lives and would eventually degrade, requiring either resupply from Earth or local manufacturing of pharmaceuticals, which is complex chemistry requiring specific ingredients and quality control. Mental health would be as important as physical health for colony survival, maybe more important, because psychological breakdown could lead to poor decisions, accidents, or violence that endangers others. The isolation, confinement, stress, and separation from Earth would create psychological pressures that would affect everyone to varying degrees. Depression, anxiety, interpersonal conflict, substance abuse if alcohol or other substances were available. These would all be risks that would need to be monitored and managed. The colony would need someone trained in psychology or psychiatry, but that person would also be part of the small community, and thus could not provide the confidential therapeutic relationship that mental health treatment normally requires. Colonists would know that their mental health provider is also their neighbor, their colleague, someone they depend on for survival, which would create barriers to seeking help. Medication for mental health conditions will be part of the pharmacy requirements, but therapy and counseling would need to be adapted to the environment. Perhaps remote counseling with therapists on Earth via delayed video messages could provide some support, though the communication delay would make traditional talk therapy awkward. Support groups among colonists, shared activities and routines that provide meaning and social connection, careful selection of crew members for psychological resilience. These would all be important preventive measures. The ultimate vision for Mars that has driven much of the enthusiasm for colonization is terraforming, the transformation of Mars into a planet where humans could live and breathe without spacesuits, where the atmosphere is thickened and warmed and enriched with oxygen, where water flows on the surface in rivers and lakes, where rain falls and plants grow in open soil under a sky that has turned from pink to blue. This vision is compelling and romantic, capturing imaginations and inspiring artwork and science fiction stories. It represents the ultimate achievement of human technological capability, remaking an entire world to suit our needs. But terraforming Mars, if it is possible at all, would be a project spanning centuries or millennia, requiring resources and commitment on a scale that human civilization has never undertaken. The colonists who go to Mars, knowing they cannot return, would not be going to a terraformed world. They would be going to the Mars that exists now, harsh and deadly, and they would spend their entire lives in pressurized habitats and spacesuits, pioneers who are beginning a process they will never see completed. The theoretical approaches to terraforming Mars generally focus on warming the planet and thickening its atmosphere, because these changes could potentially trigger feedback loops that accelerate the process. Mars is cold partly because it receives less sunlight than Earth, and partly because its thin atmosphere cannot trap heat. If the atmosphere could be thickened, the greenhouse effect would warm the planet, which would sublime more carbon dioxide from the polar ice caps, which would further thicken the atmosphere, creating a warming spiral. Some proposals suggest manufacturing powerful greenhouse gases like perfluorocarbons and releasing them into the atmosphere to amplify warming. Other ideas involve placing large mirrors in Mars' orbit to reflect additional sunlight onto the polar caps, heating them to release their frozen carbon dioxide. Still others propose impacting Mars with comets or asteroids that would deliver water and volatiles while generating heat from the impacts. These are all speculative ideas that are far beyond our current technological capabilities and would require enormous energy inputs sustained over very long periods. Even if Mars could be warmed and the atmosphere thickened to the point where liquid water was stable on the surface, the atmosphere would still not be breathable without oxygen. The released gases would be mostly carbon dioxide with some nitrogen. Creating an oxygen-rich atmosphere would require biological intervention, introducing photosynthetic organisms like algae or genetically engineered bacteria that could survive Martian conditions and begin producing oxygen from carbon dioxide. This biological terraforming will be extremely slow because even on Earth, where conditions are ideal for life, it took billions of years for photosynthetic organisms to transform the atmosphere from anoxic to oxygen-rich. On Mars, with less sunlight and harsh conditions, the process could take thousands or tens of thousands of years, even with human assistance. During this time, colonists would still need pressure suits or at minimum oxygen masks when outside, living in a partially terraformed world that is more habitable than current Mars, but still hostile to unprotected human life. The ethical questions surrounding terraforming are profound and unresolved. If Mars has any native life, even microbial life, surviving in subsurface ice deposits, does humanity have the right to terraform the planet, and in doing so likely extinguish that native biosphere? Should we preserve Mars in its natural state as a scientific resource, a place where we can study planetary evolution and search for life without contamination from Earth organisms? Or does the potential for Mars to become a second home for humanity outweigh these concerns, especially if Earth faces environmental crises or other existential threats? These questions do not have clear answers, and different people and cultures would have different perspectives based on their values regarding nature, preservation, and human expansion. The colonists on Mars would have their own perspectives, likely shaped by their immediate needs, and by living on a world where the environment is an enemy rather than something to be preserved. They might see terraforming as an imperative, as making their world livable for their descendants, while people on Earth who are not facing daily survival struggles might advocate for preservation and caution. This divergence of interests between Mars and Earth could become a source of conflict as Mars develops its own culture and identity separate from Earth. If Mars colonies are truly permanent, then at some point children will be born on Mars, the first generation of humans to begin life on another world. These children would be Martian in a profound sense that their parents, even if they spent decades on Mars, could never be. They would have no memories of Earth, no personal experience of oceans or forests or crowds of people. Their entire frame of reference for normal would be shaped by life in pressurized habitats, by seeing the sky through visors, by limited resources and constant awareness of the hostile environment just beyond the walls. They would grow up in low gravity, which raises deep questions about human development that we have no data to answer. Would children born and raised in Martian gravity develop normally? Would their bones and muscles and cardiovascular systems adapt in ways that leave them healthy for life on Mars, but unable to ever visit Earth because their bodies could not handle the higher gravity? Would their brains and cognitive development be affected by growing up in an environment so different from the one humans evolved in? Pregnancy and childbirth on Mars would be medical events with unknown risks. We know from animal studies in space that reproduction is affected by radiation and reduced gravity, with complications in pregnancy and development observed in various organisms. We have no data on human pregnancy in partial gravity or in the radiation environment of Mars. The first pregnancies on Mars would be experiments, with the colonists' children as the subjects, which raises ethical concerns that would need to be carefully considered. Should early Mars colonies ban pregnancy until more is known? Or would that be an unacceptable intrusion on reproductive freedom? How would a colony handle a pregnancy with complications that could not be managed with available medical resources? These would be difficult decisions with no good options. And the small population would mean that everyone in the colony would be intimately involved in and affected by such choices. Children growing up on Mars would need education, both in practical skills for survival and in broader knowledge that connects them to human culture and history. They would need to learn science and engineering, mathematics and communications, medicine and agriculture, all the technical knowledge necessary to maintain the colony and eventually to expand it. But they would also need to learn about Earth, about the history and diversity of human civilization, about art and literature and music, about the planet their parents came from, even if they could never go there themselves. This education would be challenging to provide with limited population and resources. There would be no schools with specialized teachers in different subjects, no universities with libraries and laboratories. Education would likely be conducted by parents and other colonists in whatever time could be spared from survival tasks, supplemented by digital learning materials and perhaps remote instruction from teachers on Earth via recorded video lessons. The curriculum would need to balance practical colonial needs with a desire to preserve broader human knowledge and culture to ensure that Martians remain connected to humanity's heritage, even as they develop their own distinct identity. The psychological experience of growing up on Mars would shape these children in ways that are difficult to predict. They might feel resentment toward their parents for bringing them into existence in such a harsh environment without their consent, for denying them the Earth they would learn about in lessons and videos but never experience. Or they might feel a fierce pride in being Martian, in being pioneers, in having a home world that no Earthborn person could truly claim. They might develop a sense of identity and purpose tied to the colonization project, seeing themselves as the foundation of a new branch of human civilization. Their relationships with Earth would be abstract, based on communication and learning rather than experience. They might view Earth as their heritage world, but not as home, the way some immigrants' children relate to their parents' birth countries, places of cultural significance, but not personal belonging. Over generations, this connection would likely weaken further, with Mars-born children of Mars-born parents having even less connection to Earth, until eventually Martians would view Earth the way Americans today view ancient Rome or medieval Europe, as historically important but not personally relevant. The financial sustainability of a Mars colony is one of the most difficult questions facing the entire colonization concept. Space missions are extraordinarily expensive, with costs measured in billions or tens of billions of dollars for each launch and each spacecraft. Establishing a permanent colony would require many missions over many years, delivering people and cargo to build infrastructure and sustain the population. Where would this money come from? And more importantly, how would the colony ever become economically self-sufficient rather than eternally dependent on funding from Earth? Without economic viability, Mars colonies would exist only as long as Earth governments or billionaire benefactors continue to pour money into them. And history shows that such support is fickle and can evaporate when political priorities change, or when economic crises demand resources be directed elsewhere. Some advocates argue that Mars could export valuable materials back to Earth to pay for imports of sophisticated equipment and supplies. Platinum, group metals, and other rare elements might be more abundant or accessible on Mars than on Earth, and could be worth shipping back despite the enormous transportation costs. But this idea faces serious challenges because launching anything from Mars to Earth requires fuel and spacecraft, and the value of materials would need to be extraordinarily high to justify those costs. Returning 1 kilogram of material from Mars to Earth might cost tens of thousands of dollars in transportation alone, which means only the most valuable substances could even potentially show profit. Furthermore, finding, mining, refining, and processing ore on Mars would require substantial industrial infrastructure that would take decades to build. In the early colonial period, when the colony is struggling to keep people alive and building basic habitats, mineral extraction and export would be impossible. By the time the colony developed enough to conduct mining operations, it might have been decades since initial colonization, and the financial benefactors would have spent hundreds of billions of dollars with no return on investment. An alternative economic model focuses on intellectual property and services rather than physical exports. Mars colonists would be conducting cutting-edge science, exploring a new world, developing technologies for survival in extreme environments, and solving problems that have never been solved before. This knowledge and these innovations could be valuable on Earth, perhaps valuable enough to justify the costs of maintaining the colony. Research data, patents on new technologies, consulting services for Earth-based industries, trying to solve hard problems. These could all provide revenue streams that do not require physically shipping materials across interplanetary space. Entertainment could also be a significant economic driver, with Earth audiences paying for access to content from Mars in the form of documentaries, virtual reality experiences, live streams of daily life, and exclusive media. The Mars One project, despite its technical failures, was built entirely on this concept, that people would pay to watch the colonization of Mars as the ultimate reality show. While that specific implementation failed, the underlying idea that Mars exploration has entertainment value to billions of people on Earth is likely sound. Tourism is sometimes proposed as an economic engine for Mars, with wealthy individuals paying enormous sums to visit Mars as the ultimate adventure travel experience. But tourism to Mars faces the same one-way problem that colonization does. If people cannot return, then tourism is not tourism. It is immigration, and the market for people willing to spend millions of dollars to permanently move to Mars will be small. Even if round-trip travel becomes possible through advanced technology, or if tourists are willing to accept the health risks and years-long commitment of a return journey, the costs would be astronomical, likely tens or hundreds of millions of dollars per person, pricing it out of reach for all but the wealthiest fraction of a percent of humanity. The market for such extreme tourism might support a handful of flights per year at most, not enough to sustain a large colony or justify the infrastructure costs. The most likely economic scenario for early Mars colonies is that they would be subsidized by Earth governments as science and exploration projects, similar to how Antarctic research stations are funded, with perhaps supplemental support from wealthy individuals and corporations who see value in being associated with Mars colonization for prestige or long-term strategic reasons. The colonies would gradually reduce their dependence on Earth by developing local manufacturing and resource utilization, closing the loops on more and more supply chains until they approach self-sufficiency in basic necessities. Advanced technology and specialized equipment would still need to come from Earth for generations, but if colonists can produce their own food, water, oxygen, fuel, building materials, and basic tools, then the supply shipments from Earth become smaller and less frequent, reducing costs to sustainable levels. Complete economic independence from Earth might never be achieved or might take centuries, but partial self-sufficiency could make colonies sustainable on subsidies that are large in absolute terms, but small relative to Earth's overall economy. The timeline of colonization. Predicting when permanent Mars colonies might be established is difficult because it depends on technological development, political will, and economic factors that are hard to forecast. As of the early 21st century, the technology needed for one-way Mars missions largely exists in principle, though it would need to be refined and integrated into complete mission systems. Rockets can deliver payloads to Mars orbit and to the surface, life support systems can keep humans alive in closed environments for extended periods. Power systems using solar panels or nuclear reactors can provide electricity. Communication systems can maintain contact across interplanetary distances. The gaps are in reliability, in scaling systems up to the necessary size, in reducing costs, and in developing new capabilities like in situ resource utilization and radiation protection that would make long-term survival possible. These are engineering challenges rather than fundamental scientific unknowns, which means they can be solved with sufficient investment of time and money. Space agencies and companies have outlined various timelines for human Mars missions. NASA's long-term plans have historically targeted the 2030s or 2040s for first crewed missions, though these dates have repeatedly slipped as budgets and priorities shifted. SpaceX has been more aggressive, with founder Elon Musk stating goals of sending uncrewed cargo missions to Mars in the mid-2020s and crewed missions potentially by the late 2020s or early 2030s. These ambitious timelines are aspirational and face numerous technical and regulatory hurdles, but they represent a different approach than traditional government space programs, with greater risk tolerance and willingness to iterate rapidly through failures. Even if the optimistic timelines prove unrealistic, they push development forward and make Mars missions feel imminent rather than distant, which helps maintain public interest and investment. The actual colonization timeline would likely involve multiple phases spread over decades. First would come robotic precursor missions, which have been ongoing since the 1960s with increasingly sophisticated probes and rovers exploring Mars. These missions map the surface, characterize the environment, search for water ice and other resources, and test technologies that would be needed for human missions. Some of these precursors might be large cargo landers sending equipment and supplies to Mars ahead of humans, prepositioning resources at the landing site so that when colonists arrive, they find habitats ready, power systems deployed, and supplies waiting. This cargo pre-positioning reduces the mass that crewed spacecraft need to carry and provides some redundancy so that equipment failures during landing do not doom the mission. The first crewed mission would likely be small, perhaps 4 to 8 astronauts in a minimalist expedition designed to demonstrate that humans can land on, survive on, and work on Mars. This first mission might still be planned as a return mission, with astronauts staying on Mars for weeks or months, and then launching back to Earth during the next return window. But even if return is planned, the experience of that first mission would inform decisions about whether return is truly necessary or whether future missions should commit to permanence from the outset. If the first crew successfully demonstrates long-duration survival, the next missions could be larger and focused on building infrastructure for permanent occupation. Each launch window, occurring every 26 months, could bring a new group of colonists, along with additional cargo and equipment. Over a decade or two of missions, the population might grow to dozens of people, and the base would evolve from a collection of habitat modules to a true settlement with extensive infrastructure. The long-term vision, extending over a century or more, would see the colony grow to hundreds and eventually thousands of inhabitants. spreading from the initial landing site to multiple settlements across Mars. Transportation networks using rovers and perhaps eventually aircraft or tunnels would connect settlements. Industrial capabilities would expand to include mining, manufacturing, construction, and eventually even semiconductor fabrication and advanced electronics. Agriculture would shift from small greenhouses to extensive underground farms or large surface facilities if terraforming progresses enough to allow it. The colony would develop its own culture and governance, its own economy and social structures, becoming increasingly distinct from Earth. At some point, a line would be crossed where the Martian colony could survive even if all contact with Earth was lost, if no supply ships arrived, if Earth itself suffered a catastrophe. This self-sufficiency would be the measure of true colonization success, the point at which humanity has genuinely become a multi-planetary species with populations that could survive independently on different worlds. Governance on Mars would be one of the most interesting aspects of colonization, because it would need to balance competing needs for efficiency, legitimacy, individual rights, and adaptability. Early missions would likely operate under mission rules designed on Earth, with commanders having authority and crew members following protocols established by space agencies. This quasi-military structure works for short missions where objectives are clear and time is limited. But as missions extend to permanent colonization, with people spending their entire lives on Mars and with children being born there, the question of legitimate governance becomes more complex. Who has the authority to make laws and rules on Mars? Do Earth governments have jurisdiction over Martian colonies? Or are colonists free to establish their own governance structures? What rights do Martians have, and how are those rights protected? The Outer Space Treaty of 1967, which has been signed by most spacefaring nations, declares that celestial bodies cannot be claimed by any nation, and that space activities must benefit all humankind. This framework suggests that Mars cannot be colonized in the traditional sense of territorial acquisition, that no nation can declare sovereignty over Martian land. But the treaty was written in an era when permanent space settlements were pure science fiction, and its provisions do not clearly address how governance would work in actual colonies. Some interpretations suggest that settlers on Mars would remain citizens of their Earth nations and subject to those nations' laws, even though enforcement across interplanetary distances would be essentially impossible. Other interpretations hold that the treaty allows for resource utilization and even settlement, as long as it does not constitute national appropriation, leaving open the possibility for colonies to govern themselves under some form of international framework or under charters granted by Earth institutions like the United Nations. In practice, Martian colonies would probably develop governance structures that reflect the needs and values of the colonists, with legitimacy derived more from practical consent than from legal theory rooted in Earth-based treaties. If a colony is funded primarily by one nation, that nation would likely exert significant influence over governance and might appoint colony leaders or establish colonial administration systems, But as the colony grows and diversifies, as children are born on Mars who never agreed to any Earth-based authority, as the practical difficulty of governing from hundreds of millions of miles away becomes apparent, local governance would become more autonomous. The colony might draft its own constitution or governing charter, establishing how decisions are made, how leaders are chosen, what rights individuals have, and how disputes are resolved. This charter might be negotiated with and approved by Earth authorities initially, but over time it would become the primary governing document, and Earth's role would fade to more of an advisory or diplomatic relationship rather than direct authority. The form of government on Mars would likely be heavily shaped by the extreme environment and small population. Direct democracy, where all colonists vote on every decision, would be impractical for routine operations, though major decisions affecting the colony's future might be put to votes. Representative democracy with the elected officials could work once the population is large enough to have meaningful representation, perhaps with an elected council or parliament making decisions on behalf of colonists. But early colonies might function more like corporate or academic structures, with leadership roles assigned based on technical expertise and with decisions made through consensus building among senior personnel. The key would be ensuring that governance is seen as legitimate by colonists, that people feel they have voice in decisions affecting their lives, because in a small, isolated community, loss of legitimacy and internal dissent could be catastrophic. Individual rights on Mars would be an area of tension between ideals and survival necessities. Earth's democratic societies value freedom of speech, freedom of movement, on privacy, and individual autonomy. But some of these rights might be constrained on Mars by survival needs. Freedom of movement might be limited by safety protocols that require coordination before EVA activities, or that restrict access to certain dangerous areas. Privacy might be limited by the small confined spaces and by monitoring of life support and safety systems that track people's locations and activities. Freedom of speech might be tested if someone's words or actions undermine group cohesion or safety, in a way that would be tolerated on Earth, but is seen as dangerous in the colonial context. The colony would need to find balances that protect essential human rights, while acknowledging that some Earth normal freedoms might not be sustainable in the Martian environment, at least not in the early colonial period. These balances would likely be spelled out in the colony's governing charter, and would evolve as the colony grew and as technology improved to make life safer and less constrained. Over decades and centuries, if Mars colonies survive and grow, a distinct Martian culture would inevitably emerge, shaped by the unique environment and history of the colonization experience. This culture would have roots in Earth cultures, brought by the colonists from various nations and backgrounds, but would synthesize and transform those influences into something new. The shared experience of living in a hostile environment where survival requires cooperation and technical competence would create strong common values around community, education, and pragmatism. Here, the frontier experience of building a new world from scratch would create narratives and stories that would become foundational myths for Martian culture. Stories of the first landings, of crises overcome, of pioneers who gave their lives so that the colony could survive. These stories would be told and retold, evolving in the retelling, becoming the cultural touchstones that define what it means to be Martian. Language on Mars would initially be whatever languages the colonists brought with them, likely English as a common language, since much of early space exploration has been conducted in English, but also Chinese, Russian, Hindi, Arabic, Spanish, and many others depending on which nations and populations contribute colonists. Over time, if the colony is diverse, a lingua franca would emerge, probably English-based but incorporating words and grammar from other languages, evolving in isolation from Earth into a distinct Martian dialect, or eventually a distinct language. Technical terminology would proliferate as colonists develop words for things and concepts unique to Mars, for equipment and procedures and environmental conditions that have no Earth equivalents. The physical environment would influence language, with metaphors and expressions drawn from Martian experiences rather than Earth ones. Colonists might measure distances in meters to habitat rather than miles or kilometers. They might measure time in sols rather than days. They might develop expressions based on dust storms and low gravity and the pink sky. Expressions that would be meaningless to Earth speakers but perfectly natural to Martians. Art and cultural expression on Mars would be shaped by the constraints and by the unique perspective of living on another world. Visual art might focus on the Martian landscape, capturing the alien beauty of red deserts and distant horizons, or might focus inward on human experiences in confined spaces. Music could be created and performed with synthesizers and recorded instruments brought from Earth, but live performance with acoustic instruments would be limited by what could be transported and maintained. Literature would flourish because writing requires no special equipment beyond recording devices, and Martian authors would have unique stories to tell about colonization, about life in extreme environments, about separation and adaptation. These artistic works would be shared with Earth via data transmission, are contributing to human culture broadly, but would also serve important functions within the colony by expressing shared experiences, by preserving history, by providing entertainment and meaning in lives that might otherwise be consumed by survival tasks. Religion and philosophy on Mars would be fascinating areas of cultural development. Some colonists would bring religious beliefs from Earth, continuing to practice Christianity, Islam, Hinduism, Buddhism, and other faiths in the Martian context. These practices would need to adapt to the environment with rituals and observances modified for life in habitats. The direction of Mecca for Muslim prayers would be an interesting question when you are on Mars, requiring complex astronomical calculation to determine the direction to Earth and then to specific locations on Earth. Religious communities might find deep meaning in the colonization experience, seeing it as divinely ordained or as part of a spiritual journey for humanity. Other colonists might find traditional religions less satisfying in the face of Martian realities and might develop new philosophical or spiritual frameworks better suited to their experiences. There might emerge a distinctly Martian philosophy or worldview shaped by the knowledge that you are part of an endeavor larger than yourself, that you are building something that will last beyond your lifetime, that you have separated yourself from humanity's birth world permanently in pursuit of a greater goal. This could create a sense of purpose and transcendence that functions similarly to religious belief, even if not formally organized as such. One of the strongest justifications for Mars colonization, beyond the species survival argument, is the scientific value of having humans permanently stationed on another world conducting research. Mars is a natural laboratory for planetary science, a place where we can study geological processes, climate, atmospheric chemistry, and potentially even biology in an environment different from Earth. Robotic missions have been extraordinarily successful at Mars science, with rovers like Curiosity and Perseverance conducting sophisticated experiments and sending back enormous amounts of data. But humans can do science that robots cannot, or can do it much more efficiently and with greater adaptability. A human geologist on Mars could explore an area in a few days that might take a rover months to traverse. One could make judgment calls about which samples to collect based on training and experience, could respond to unexpected discoveries in real time without waiting for instructions from Earth. The search for life on Mars would be dramatically advanced by human presence. While no life has yet been found on Mars, the planet had liquid water on its surface billions of years ago, and conditions then might have been suitable for life to emerge. If life did develop on Mars, either independently or by transfer of microbes from Earth via meteorite impacts, remnants might still survive in subsurface ice deposits, or deep underground where conditions are less harsh. Finding such life would be one of the most important scientific discoveries in history, answering the question of whether life is unique to Earth or whether it arises wherever conditions permit. Humans on Mars could drill deeper, explore more sites, conduct more sophisticated analyses than robots could do, and could follow up on unexpected findings with immediate additional investigation. The discovery of current or fossil Martian life would also raise profound questions for terraforming, as mentioned earlier, because it would mean Mars has its own biosphere that would be disrupted or destroyed by making the planet habitable for humans. Astronomy and astrophysics would benefit from observatories on Mars, particularly radio telescopes. Mars has a thin atmosphere that does not block radio waves the way Earth's ionosphere can, and Mars has no radio interference from human telecommunications that plague Earth-based observations. The far side of Phobos, Mars's larger moon, would be an even better location for radio telescopes because it would be permanently shielded from Mars itself as well as from Earth, creating the quietest radio environment in the inner solar system. Colonists could construct and maintain telescopes on Phobos or on the Martian surface, conducting observations of distant galaxies, pulsars, and the cosmic microwave background radiation that carries information about the early universe. Optical telescopes on Mars would not have significant advantages over space-based telescopes like Hubble or James Webb, but they would be easier to maintain and upgrade with humans present, and the lower gravity would make building large structures easier than on Earth. Mars would also serve as a laboratory for learning how to live on worlds beyond Earth, developing technologies and techniques that would apply to colonization of asteroids, moons of the outer planets, or even eventually exoplanets orbiting other stars. Every challenge overcome on Mars, every technology developed for Martian conditions, would be a step toward understanding what humanity needs to become a truly spacefaring civilization. The experience of Mars colonists would inform future missions. Their failures would teach what to avoid. Their successes would show what is possible. In this sense, Mars colonization is not just about Mars, but about whether human beings can exist permanently anywhere other than Earth. About whether we are forever bound to the world that birthed us, or whether we can adapt to new environments and continue to thrive. The ethics of sending humans on one-way missions to Mars, particularly the ethics of allowing people to volunteer for such missions, deserves careful consideration. There is a strong argument that competent adults should have the freedom to make decisions about their own lives, including decisions to take extraordinary risks in pursuit of goals they find meaningful. Mountain climbers accept significant risk of death to summit peaks. Test pilots flew experimental aircraft knowing that many of their predecessors had died. Explorers throughout history have ventured into unknown territories with low probabilities of survival. Mars colonization could be seen as an extension of this tradition, an informed choice by people who understand the risks and accept them in exchange for the opportunity to be part of something historic and important. From this perspective, prohibiting people from volunteering for one-way Mars missions would be paternalistic, denying them agency and treating them as children who cannot be trusted to make their own decisions. But there are counter-arguments that should be considered seriously. One is that the risks of Mars colonization are so extreme and so permanent that informed consent is questionable. Can someone truly consent to spending the rest of their life in a hostile environment with high probability of painful death and no possibility of rescue? Can they foresee how they will feel after years of isolation and confinement? Whether they will regret their decision when it is too late to reverse it? The psychological research on affective forecasting shows that humans are poor at predicting their future emotional states, that we systematically underestimate how much we will adapt to circumstances and overestimate how happy or unhappy we will be. Someone volunteering for Mars in the excitement of selection and training might feel very differently 5 years into their time on Mars, when the novelty has worn off and the reality of permanent exile sets in. Yet they would have no recourse, no way to undo the decision, no escape. Another ethical concern is the impact on people who remain on Earth, particularly family members of Mars colonists. While the colonist has chosen to go, their parents, siblings, children, friends have not chosen to lose that person permanently. The grief and loss experienced by those left behind would be substantial and would not be adequately addressed by the colonist's choice. This does not mean that people should be prohibited from going to Mars out of consideration for others' feelings, but it does mean that the decision has ethical dimensions beyond just individual autonomy. Society permits and even honors choices like military service or hazardous professions that risk leaving families without loved ones. But those choices are generally made in service of protecting those families or serving the community. The benefit of Mars colonization to humanity is more abstract and distant. which might make the sacrifice harder to justify to those who bear the emotional cost. Children born on Mars raise the most difficult ethical questions because they have no choice in the matter. They are brought into existence in an environment that is hostile and dangerous, with limited opportunities and freedoms, and they can never leave. Is it ethical to create a life under such circumstances? Some would argue that, as long as the life can be one worth living, with love and meaning and positive experiences despite the hardships, then it is no different ethically than people choosing to have children in difficult circumstances on Earth, whether in poverty, war zones, or areas affected by climate change. Others would contend that there is a qualitative difference, that Mars is not just difficult, but fundamentally unsuitable for human flourishing, that children raised on Mars are being subjected to an experiment without their consent. These are difficult questions without clear answers, and different ethical frameworks would lead to different conclusions. A utilitarian might focus on the potential benefits to humanity's long-term survival and conclude that Mars colonization is justified even with its costs. A deontologist might focus on the rights of individuals and conclude that creating permanent exiles or bringing children into such an environment violates those rights. Religious ethics would vary depending on beliefs about humanity's role in the universe and our relationship with creation. The choice to pursue Mars colonization through one-way missions is ultimately a choice about what kind of species we want to be and what kind of future we want to pursue. It is a choice that involves risk, sacrifice, and permanent commitments from the individuals who become colonists. It is a choice that requires sustained investment and support from societies on Earth that will not directly benefit for generations. It is a choice with ethical complexities around consent, risk, and the well-being of those affected. But it is also a choice that could determine whether humanity survives in the very long term, whether we become a multi-planetary species capable of persisting through catastrophes that might befall Earth, whether we continue to push boundaries and explore and grow, or whether we remain forever on one world with all our eggs in that single basket. The argument for Mars colonization, despite its one-way nature, rests on several pillars. First is the survival argument that a second, independent population of humans on Mars would serve as a backup for our species, ensuring that disease, nuclear war, asteroid impact, or environmental collapse on Earth does not mean human extinction. Second is the practical argument that one-way missions are technologically and economically feasible with near-term capabilities, while round-trip missions might require technologies that are decades or centuries away. Third is the aspirational argument that humanity has always been an exploring species, that we are driven to see what lies beyond the horizon, and that Mars represents the next horizon in a journey that has taken us across Earth and to the Moon and should continue outward. Fourth is the scientific argument that Mars offers discoveries and knowledge that could benefit all humanity, and that human presence would accelerate that scientific return dramatically compared to robotic missions alone. The arguments against are also substantial and deserve consideration. The cost is enormous, with resources that could be used to address problems on Earth instead being diverted to space exploration. The human cost to colonists and their families is severe and permanent. The technological and logistical challenges are immense, with many potential failure modes that could result in deaths. The ethical questions around informed consent, around creating Martian-born children who never chose their circumstances, around potentially contaminating or destroying any native Martian life. These are all serious concerns that should not be dismissed. The political and social challenges of maintaining support for multi-generational projects, of governing across interplanetary distances, of managing the relationship between Earth and an increasingly independent Martian colony. These could create conflicts and failures that undermine the entire endeavor. Ultimately, the decision to pursue Mars colonization will be made through a combination of governmental policies, corporate investments, technological developments, and the choices of individuals who volunteer to be colonists. It will not be a single moment of decision, but rather a series of choices and investments that accumulate over years and decades, each one building on the previous ones, until humanity finds itself committed to a path that would be difficult to reverse. We are already on this path to some degree, with robotic missions to Mars continuing and accelerating, with space agencies and companies developing technologies applicable to human Mars missions, with public interest and support for Mars exploration remaining strong despite the costs and challenges. The question is not whether we can go to Mars. We likely can within the next few decades, but whether we should, and if so, on what terms, and with what safeguards for the people who will spend their lives there. The colonists who choose to go to Mars, knowing they cannot return, will be making a choice that defines them as profoundly as any decision a human can make. They will be choosing to leave behind the world that birthed our species, the blue oceans and green forests that our ancestors knew for millions of years, the comfortable gravity and protective atmosphere that shaped every aspect of how our bodies and minds work. They will be choosing instead a world of red dust and thin air, of radiation and cold, of endless work maintaining systems that keep them alive in an environment that wants to kill them. They will be choosing separation from everyone and everything they have known, with communication reduced to time-delayed messages and relationships reduced to memory. They will be choosing to become test subjects in an experiment about human adaptability and resilience, knowing that they might fail, that the colony might collapse, that their sacrifice might be for nothing. But they will also be choosing to be pioneers in the truest sense, to be the founders of a new branch of human civilization, to be the first of a lineage that might one day spread across the solar system and beyond. They will be choosing to work on one of the greatest challenges humanity has ever attempted, to transform themselves and their environment in ways that push the boundaries of what is possible. They will be choosing community and common purpose in a way that modern Earth life rarely provides, bound to their fellow colonists by shared danger and shared goals. They will be choosing to live with intention and meaning, knowing that their efforts matter, that they are building something that will outlast them, that future generations of Martians will look back on them as the ancestors who made their world possible. They will be choosing a difficult life, but not necessarily an unhappy one, not necessarily a life less full of love and joy and accomplishment than they would have had on Earth. The first footsteps on Mars by settlers who will never leave will mark a transition point in human history as significant as the first footsteps of our ancestors leaving Africa, as significant as the first farmers planting seeds, as significant as the first ships sailing beyond sight of land. Those footsteps will say that we are no longer solely a species of Earth, that we are becoming a multi-planetary civilization, that we accept the risks and costs and sorrows of expansion because we believe the alternative is stagnation and ultimately extinction. Those footsteps will be heavy with the weight of permanence, of commitment, of irreversible change. The dust kicked up by boots on Mars will settle back to the surface and will be blown by winds across the plains and valleys of that ancient world, mixing and dispersing, becoming part of Mars just as the colonists themselves will become part of Mars, their atoms eventually joining the red soil, their legacy carried forward by those who come after. Looking up at Mars from Earth, that bright red point in the evening sky that has fascinated humans since before history began, we will know that there are people there, people living and working and maybe singing and certainly dreaming under that pink sky. We will know that those people can see us too, can see Earth as a blue star in their sky, and that they carry humanity forward in a new environment with new challenges and new possibilities. We will know that whatever happens to Earth, whether we solve our problems or succumb to them, humanity exists in at least two places, that we have taken the first steps toward ensuring that our species and our culture and our accumulated knowledge can survive beyond the fragility of a single world. And maybe that knowledge, that expansion, that commitment to the future and to growth and to the endless human drive to explore and to understand and to create, maybe that will be worth the price that the Martian colonists pay in never coming home. Maybe their choice will inspire us to make better choices, to think longer term, to care more about what we are building for those who come after. Maybe the permanent separation between Earth and Mars, between the world that was and the world that could be, will teach us something profound about what it means to be human and what we are capable of when we commit ourselves fully to a vision beyond our individual lives. The red planet waits in the darkness, patient and ancient, and ready to be transformed by human hands and human will. The choice is ours whether to answer that call, whether to send our brothers and sisters and children on a journey with no return, whether to begin the process of becoming a civilization that lives on multiple worlds. It is a choice we cannot make lightly and should not make without full understanding of the costs and risks, but it is also a choice we may need to make if we want humanity to persist through the millennia and ages to come, if we want to be more than a footnote in cosmic history. If we believe that consciousness and culture and love and art and science are worth preserving even at the price of exile for those who carry those things to new worlds. Mars offers us that choice, written in red dust and thin air and distant sunlight. What we choose will echo through the centuries, shaping not just the lives of colonists, but the entire arc of human civilization. And whatever we choose, those who go will carry Earth with them in their hearts, even as their footsteps trace new paths across alien soil, even as they breathe air they manufacture themselves, even as they look up at an unfamiliar arrangement of stars and make their peace with never going home. They will be the bridge between worlds, between what we were and what we might become. And their lives will be the price and the promise of humanity's future among the stars.